The River Germany.
Let's.
The guy who's now.
You left Let's.
Oh, you. I joined this year. Mwenja.
This year. Mwenja, yeah, that's Let's.
Oh, okay. So, you mean the legacy?
Black.
I love reading textbooks and writing about software and software engineering concepts in general. I have a blog, that's the cover. Okay, so on to the details. I hope the theme found was up.
How about you just summarize everything in a way that a 5-year-old can understand?
Okay, so, but now the whatever video.
Make that.
Okay,
summarize.
Okay, so storage engine it's a component within a DBMS. See, everyone knows that DBMS, MySQL, Postgres, yeah. But now beneath it, so a DBMS is the entire thing. But within the DBMS, there are multiple components that really call the DBMS. Think of the processor, the storage manager, the transaction manager. Then at the core of everything now lies the storage engine. So storage engine, they're the most critical component within a DBMS, and the writing of raw data into the underlying disk storage, and also memory. Remember for database or DBMSs, we either have the memory first DBMS or the disk first DBMS. Okay, so storage engine, as I've said, is the most critical component within a DBMS. Then another thing I need to clarify is the difference between a database and a database management system. So when we talk of database, most people refer to the database management system as the database. So DBMS is the software that allows you to read and write your data. But a database is the actual data that you are reading and writing via the DBMS. Then, okay, I have a small analogy to maybe make it simpler to understand. So think of it as a restaurant, whereby the different flavors of food within the kitchen is the database. It's the data that your customers are actually interested in getting. Then the kitchen is the storage engine. Remember, in the kitchen you're when okay, so now the kitchen is the storage engine. It's the one that organizes everything. Then the entire restaurant, you need the DBMS. Now everything's scaffolded together, brings you the restaurant, which is the DBMS.
I think to make this like a bit clearer for everybody, and your storage engine gives very strong guarantees to chips.
Yes.
Like when a chef says nikitungu and nikeka pilipili tabia of a certain way, that's his storage engine. However, the chef cooks his ingredients, that's it.
Yeah. Then another thing, so we add other components. You can add a transaction manager or the query processor. So you can think of the waitress and the waiter and the manager, how what they come together to form that, to bring the restaurant, to make it what it is. Yeah. Okay, now TidesDB. I feel like I should change the font. Yeah. Font. Zoom. Okay. Better. Okay, now what's TidesDB? TidesDB is an open source, but not a free open source.
Imports.
Free.
MongoDB.
No, not like MongoDB. It's a free open source embeddable key value storage engine. The reason why it's embeddable is because you can plug it directly into your application. So if you have a C, now it's suited in C. So if you have a C program, you don't need to install MariaDB. You can get everything that MariaDB offers, but not via library. You only do include the path to your header files. If it's a web application, it's bindings. It has a good file that you can generate bindings for C, so for Rust, C++, Go. So if you're building on any language, then you can easily plug it into your application without having the hassle of installing the infrastructure software kama Postgres or any other database management system. So it's based on log structure matrix, like traditional OLAP database engines built on B-trees. So yeah. So, and in the course of the presentation, we come across a term that might be new to some of us, na shape library. Yeah. So TidesDB log key value storage engine is based on log structure matrix. So a log structure matrix is a data structure. Data structure whereby you see, logs, a log file. So basically a log structure matrix behaves like a log file. You append to it. You don't do inline updates. If you write to a log file, how you offset, like you're going back to the start of the file and to the end of the file. You're always appending to the end of the file. Now, yeah.
Can I change it?
Okay.
So to explain your stuff in a way you can easily understand. Typical DBs like in MariaDB, MySQLDB, whatnot. When you read like the paper, they usually give you strong guarantees ACID. Yeah? So historically, utapata under the hood wanafanya vitu kama BSD trees. So yeah, the B trees, because B trees have some very nice properties that fit in very well with ACID compliance. So why did we don't say, okay, I've never heard of this before, but why did you say they use a different underlying structure to give you the stuff is about stock?
So yeah, thanks. So LSM. So the contrast with B trees is that for B trees, B trees are optimized for reads. The reason why they're optimized for reads is because you have indexes. So indexes are these in-memory data structures in store maybe a key and an offset to where the actual value is stored on disk. So that's why for reads you only go to the in-memory data structure, that's the index, with the ID, with the key. The key will be the primary key to a table, anything that the database might choose to use as a key. But for log structure matrices, easy to optimize for writes. The reason why they optimize for writes, one, because they are up and running. Remember, okay, there's this point up the second one that builds on whatever, on the reason why we choose log structure matrices instead of buildings. So LSM trees, they are crazy fast for writes because you only append. Remember, the slowest operation on a disk, on a hard drive, is seeking. So for B trees, every write operation does a seek on the disk. But remember, seeks are way slower because for different types of solid drives of hard drive, you're gonna HDD and SSD. For HDD, it uses a different technology from SSD, whereby you have a hand that in a spin around. So the hand that spins around, it needs to spin. So kuna some circular segment, then you have a hand that spins. So the more this hand spins, the more it increases the disk latency. That's why for HDDs, the writes are way slower than reads, because for write lazima you seek to the location that you want to write to, then you write. But now for SSD hakuna like si magnetic, inatumia I'm not well versed with the specific technology inatumia, but inatumia concept ya flash memory, whereby kuna pages and you don't have a spinning hand. Inakuja tu that it will locate the specific page. Kama inaweza write itaandika, kama iko na content inaweza erase before iandike. Then I used OLAP. So OLAP means online and analytical processing. Think of Postgres, MySQL. Easy and remember for analytics, you want to run like your workloads are real, because yes, you can data behind, but you need to run queries that zina pull data and you aggregate and all that. But now the opposite of OLAP means OLTP, online transactional processing storage units. So easy happen whereby you have a workload that's going to be right here. Tuseme kitu kama you see how you request Uber ride. I assume that the database unatumia ni OLTP. It's optimized for a right-head workload, because if you request Uber, you're generating data that needs to be written somewhere. So the database that they're using needs to handle close to couple of millions of transactions per second. Yeah. Okay. A question here is, what's the slowest operation on this specifically HDB? C. Because magnetic arm lazima spin around, locate the specific page you want to read, then you read. This is why we left out SSDs, because the latest difference between reads and writes on SSD, it's negligible, because it's the same technology for both. Kuna spinning arm. Then embeddable, because you can include it as a library within your project, you don't have it installed in infrastructure to you can use the storage engine directly, because it guarantees you acidity, durability, chronicity, whatever a fully fledged database management system does, the storage engine will in a power up. So you can actually embed the storage engine directly into your application. Or if you're building a DBMS, you can embed this as your storage engine. So TidesDB currently for MariaDB, it has a plugin called TidesSQL. You can search up TidesSQL. Near pluggable storage engine for MariaDB. So instead of InnoDB ni kama InnoDB, like it's the traditional variant which is optimized for heavy workloads and DB. Also, RocksDB. Yeah. So RocksDB recently the MyRocks plugin for MariaDB was archived. So this is the best bet that anyone mwenye anataka kufanya retrieve workloads by MariaDB has. It's called TidesSQL. Now this is kind of simplified, not so simplified much. So the different components, you have a column family. Column family for a column family naturally. It's not used a lot, but utapata that the LSM oriented database engines now this is TidesDB, CockroachDB with their Pebble storage engine wanatumia a column family. So column family in the traditional world, the read-oriented databases, you could think of this as a table. So column family near key value namespace with configurable behavior. So a column family has a writer headlog, has a name table, a queue, and has several SS tables. Writer headlog, one. Anyone? Yeah, writer headlog. So if you want your database to guarantee durability and integrity, you have to think of a wall first. So a wall ni an append only you can say it's an append-only file, whereby any transaction if your database receives a request to write something to the disk, and you say that for LSM storage engines, you got to memory first. So LSM storage engines, how write works on a transaction upon commit, it is written to the writer header, then subsequently written in memory. There is this mutable. A mutable near in memory with the structure. Okay. Before that, so a write comes in and equal to the writer header. The reason why we append it to the writer header first is because when a system crashes, these power loss, if your data was only lying in memory, it will be wiped out. So memory is volatile, inatumia RAM. So if it's not persisted anywhere, itakuwa flashed out, you lose everything. But if you first have it written in the write-ahead log, the write-ahead log is on disk. So every write operation first commits to the write-ahead log, inakuwa synced, then later to the mutable. So it guarantees the durability such that even if your application crashes, then you can recover the state of the data just before the commit that crashed from the write-ahead. Yeah. Any questions?
Operation do it on this direct.
Because disks are stable. There is
Why did you go into that approach?
Okay. So your question is why would we want to write to the write-ahead log first?
Yes.
Before?
Yes. And still in a writing process.
Okay. So one is because operations we don't commit to. Okay, let me put it this way. We want to take advantage of writing in memory. Okay. So if we had skipped write-ahead log, so to make a write-ahead log from the write part. So a write comes in a written to mutable initial. Like for a write, for Postgres, if you're writing something, then you guarantee that it acquired to disk within that single operation. That's not the case for LSM storage engine. It does the opposite. So write Kikuja, it and equal to the one first to ensure that this operation is durable, then in acquired to memory. As long as it was stored in memory within this structure called the mem table, your transaction in a backing. Your transaction is successful. Like it doesn't need to do a subsequent write. You can, as long as it's a supported object store backend. Currently, kuna GCP in S3. You can plug in the object store backend into TidesDB. What this gives you is close to infinite scale. You can scale up to database. Like you're not limited by the actual storage that provider upon you are limited by the limit of the object store backend. For example, okay, this gives you a petabyte scale. Like you can, unaweza kuwa na inaweza gazeta as you see the different object stores zinakupatia different guarantees. So whatever your object store backend states that you don't limit, that's where you become. Column families, the key value namespaces with their own configurations, and non-blocking. This is actually an important thing. Non-blocking write and reads. So write don't block reads and reads don't block write. Tunatumia position independent I/O using this system called period and period. So period and period. Okay.
So in terms of features, in this exercise, we have the three categories of features. Number one, people who work with systems. Number two, people who are just beginning their careers. Number three, people who are like exploring. How can you simplify why people are going to look at TidesDB, those three clusters, in a way they can relate to? So in simple language.
In simple language. Okay, I'll
Start with the production tier, and then entry-level people, and then just like curious people who are just beginning to learn about it.
Okay, there is involved in production tier systems.
Simple language.
Okay, there is involved in production tier systems. You want you analyze your workload, and you're seeing that there's a bottleneck that you are handling way too more writes than reads, but your current database implementation doesn't guarantee. Only guarantees you good write performance because unatumia MariaDB, MySQL or Postgres. So for the curious guys when you're now who are working on production systems, you want maybe after analyzing your workload now you need something that guarantees you extremely high write performance compared to reads because the trade-offs have pushed you towards the right heavy path. So
in
that's
other
the
words,
first
to
thing.
simplify it,
Yeah.
for production people in this crowd, this is another thing you can look at to explore the intelligence. Let's go to the next tier.
The next tier you call me the
Tier,
entry
people
level.
are just like very entry level people, so like mid-level people who have been to work with production systems like that, but you're just getting there. You just got your first job, like you're just from uni, figuring this stuff, you have clients here and there. Why would they explore TidesDB?
Okay, I'll give an example with myself.
Yeah.
So I joined Server Informatics. Sijamaliza shule bado, but I joined Server Informatics last year February. I didn't have interest in like the database stuff, so I would consider myself entry level last year. Then something sparked in me, so I came across a book I think from TidesDB. It's also some database company, and it sparked an interest in me. So as much as nilikuwa someone entry level, akili yangu ilikuwa inafikiria that now this is what I should be doing. Yes, in say entry level it might not directly apply to their course of work, but it might give you a career trajectory towards going somewhere. So that's what I would say from
If I can translate it for you, so for people who are like very entry level to this type of stuff, as you get into this type of stuff, he makes a very strong claim that exploring this thing will expose you to a lot of DB internals. Learning about write-ahead loads and all that fluff that will be very beneficial for you in your future career and how you make decisions. Is that accurate?
Yeah, that's accurate.
Sir, to the people who are clueless.
Well, then another thing here, there's something called mechanical sympathy. You can look it up.
Yeah.
It tells you that F1 drivers, for you to be a good F1 driver, you don't need to
Have the tools.
know the tools, but you need to have an intuition on how it works. Yeah.
So I think that answer also covers it for like the people who are just very new to Linux.
This is a rough rundown on the internal components. We have something called a skip list, block manager, filter, buffer, clock cache, and manifest. So a skip list is what you use to implement the main table. Remember, main table is the in-memory is the structure that stores that all writes go through before being merged into becoming SS tables. So it's a probabilistic data structure implementing the main table. The trade-off made here, choosing it over a real or red black trees is due to the free potential and ease of implementation. You'll see most of the data structures that you're listing here need free data structures. But you don't need to hold atomic logs, you don't need to hold mutex logs or something like that, because logs cut performance. Compare and swap. It's a technique for atomicity, whereby you compare two memory locations. If the compared value is the same as whatever is on the current memory location in the swap, otherwise you will try, because it means that some write came in or something changed. Block manager, this is the abstraction for any IO related operation for the storage engine. So we have two kinds of IO operations. We can writing to the wall and writing to the system. So every write goes through the block manager. It's log free, append only, abstraction. Remember the log structure, so you only append to the end of a file. So that's why append only. Then writers use different depending on the specific write operation. If it's a read operation, it will be a positional read system called period. If it's a write operation, it will be a position independent write called a period. So it allows for concurrent reads or writes. Recently, there's a bug we fixed around this. We named it the one-hole problem. So what happens is a thread comes in because it's multiple. You have multiple concurrent writers. A thread must reserve space. But what happens is the thread reserves the space, but the write operation fails. So you can some segment within the reserved space that's not filled. Then during recovery, what happens is if you got an empty space, you skip. So there was possibility for data loss when the recovery worker encounters a hole within the SS table. Then block writes use this is another system called p-write read. So the structure of a block ni kuna header, kuna body na kuna footer. So initially what used to happen, we used to issue three different system calls, writing the header of the block, writing the actual content of the block, the data being written in the footer. But we came across p-write read that gives you scatter gather vector IO. Instead of going back and forth to the kitchen kuchukua things one by one, nina once unachukua kila kitu ninarudi. So that's now scatter gather IO. Then also we have checksumming. Checksumming ni for data integrity to ensure that the data that was stored. So when you write data, you computer checksum, it's stored in the block. When you read the data, you compute checksum with the retrieved value. You compare the two checksums. Kama zina match, then iko sawa. Kama has matched, then it's a corruption at this level. Also, if data sync. So this is what our friend was saying, that tuna JavaScript utafanya file.write, but that not specifically JavaScript, but any language utafanya file.write ama OS.write, but that doesn't guarantee you that data has been written to disk. It only guarantees you that data has been copied from the application level, the user space, into the OS page cache in the kernel space. So kuna hizo two different modes, the user space and kernel space.
So that writing to disk was story here a couple of years back, 7 years back. I inherited a bunch of spinning disks, but here in Kenya, I didn't know this thing. So I did like a Python thing with open F-write, but in everything then flash. This thing, no, not closes the context. Like flash guarantees that memory has been written to disk. Yeah, like I was copying over I was using threads and I was copying over Steve to separate things. And I mean for 40 GB. This thing crashes because some other person was running some heavy thing in the compute cluster. And I remember I'm like, say just restart from where I started. And I'm looking at it and I'm like, I did not write it. Like out of the 40 GB I just written like freaking 12 GB, and I was like, it took me such a long time to figure out this flash thing and to also figure out that there's that system called that does the flash and where the kernel handles it here. And the context for that is I was building like Sapien indexing. If you've done like many GNU projects with their email thing, they usually use Sapien. So the way of building like a Sapien index that's like around 156 GB, and around 4 GB of like this thing kept crashing, but I do not have that. So it's very subtle and very annoying.
So for durability guarantees for the SS table, you have to do an F-beta sync. Okay, F-beta sync is specific to Linux. Specific to Linux distributions. I go for Mac, I go for Windows. So for Mac and Windows, tunapaki to F-sync.
And also for a lot of these Linux system calls, if you ever have the opportunity to work with a BSD, just know that Linux is not physics compliant. Maybe except Fedora. Fedora isn't even physics compliant. So a lot of system calls that would work on Linux, if you ever work on a BSD system, because you assume that everything is Unixy, it just won't work. Heads up. So a lot of tooling in Linux won't work outside Linux. It's tooling is good. But in BSD, FreeBSD, NetBSD, and the ilk, it just won't work. And you have to do a lot of info.
Yeah, so what happens is, okay, for TidesDB to have compatibility there, that so it's cross-platform across any distribution, Mac, Windows, any Linux, FreeBSD, Firefly, any distro. So okay, in our pipelines, we like 40. We run tests on over 40 platforms in a such cross compatibility layer. So okay, we chose a data sync over F-sync to minimize this bandwidth consumption. Remember, it's not the only thing that's happening in Amazon. Okay. If you're ready to this, you're not the only one that's writing. So if your thread in a lot of this bandwidth, it will connect the other threads that are writing or reading. So that's why we chose a data sync, because the data sync can only transfer we only transfer the data that will be required for a successful subsequent trip. And like F-sync the transfer killer key to modify time, query time, like a lot of stuff. Then there's also an F-sync. Now F-sync in a flash killer key. So if you call sync, not F-sync. Sync, F-sync, the F in a manager, the file descriptor. So it only flash the data that's tied to the file descriptor. If you do a sync, it will see that you got the entire page cache, it can bring it into this. So utapata that mbona write operations zangu ziko so slow, that is because you're doing a sync, because inachukua even other open file descriptors and say any other user in the system kama alikuwa na write itapita nayo. Also KLog, VLog. Remember back there we mentioned something called whiskey, separating keys from values. So okay, KLog, VLog, they are tied to an SS table. SS table in logic, it's logical, like unlike other systems in logical, so you don't really have a natural file for this called SS table. What you have is KLogs and VLogs that are linked together. So for any key value pair, if the size is less than 512 MB, it will be a KLog. Any key value pair greater than 512 MB, the KLog will only store the offset. Sorry, we only store the key and the offset to the value which is stored in the value log. Yeah. Any question of that?
I was wondering how you are calculating the writers.
Concurrent. Yeah. Oh, see, so okay, it's remember it's append only. So for a given file, you want to have a writer seeking. I'm writing to a different offset out of the end of file. Then what happens? We do each and every thread in a file has this reservation. So as a thread, I'm going to write 10 kilobytes. This. What I'll do, it's an atomic operation. To store the current file offset. So the current thread is the current file offset. Then in the same operation, it will increment the file offset. Then store it back. So it's more of a compare and swap operation. You narrate the current file offset, you increment it, then you update the file offset, such that any subsequent thread in Akuja will read the updated file offset. Like you can never have two two threads competing for the same offset within the file. Yeah. Because the offset reservation is an atomic operation. The atomic operations happen as single CPU instruction. So it either inamaliza ama it's like it never happened before. Yeah. So the thread in a reserved space. So in our minds we assume that a write operation can never fail. So if it fails, it will either write some few bytes or no bytes at all. No bytes at all.
I'm just curious, this bug, was it like an upstream bug, or was it like a bug you guys faced that work and then you have to upstream the fix?
No. See, okay.
Or it was an issue you guys faced and then you went to like the issue log and then like, yeah.
Actually, I'm the one who faced the issue and I fixed for the issue.
No upstream?
Yeah.
Hey, yes.
I think I wrote a blog around it called the world problem. So you wanted to know when you occur. So the thread in the reserved space from offset 10 to offset 20. As a developer, I expect it to fill the offsets. Because during recovery, maybe application will crash. So during recovery, the recovery thread itapitia multiple access tables. Ikijaribu compute the checksum that was stored na the new checksum that has been computed. But itapata a file offset yenye iko na garbage hapo ndani, like nothing written in it. And what used to happen, it can encounter such garbage in a skip USS table. So meaning, if the whole occurred at the beginning of the file and at the middle of the file, you are losing data for that file. Yeah.
So how do you do this?
So okay, the first thing that you notice that will result into an incomplete write is something called una signal called an interrupt signal. So if the kernel fires an interrupt signal, it will interrupt the current write operation. So the first thing ilikuwa ni kuzima the signal during a write operation, so that you mask. Linux gives you a way to mask signal so that a write operation ama disk operation isn't interrupted by any signal. So that was the first thing to ensure that it may still occur, but its chances are really minimal. Then for the other operation, for the other stuff, the recovery thread skipping a valid, like email counter hole, then in a channel your file in the next file. So it can count a hole, it tries as much as possible to determine the next offset. So that because moving to the next block depends on the current block. So kwa block tuko na header body na footer. The header contains the block. So if the write operation fails after writing the block size, then you can advance past it. But now the answer to that means if a write operation failed before writing the block size, then we are not guaranteed where the next offset is answer. So we can't advance now. You're in the line.
Can I give you a similar answer that you can do? Films are more production, rates as kazi. Na docs anafuata docs. Watakuuliza maswali ngumu hapo, like wait a minute, we're doing everything right. Ukaingia deep. That's what it is.
So that's all yangu.
You can ask as a follow-up.
Yangu ilikuwa kama kuna space but what is edit hiyo, how do you feel it ama inabaki?
No, you don't feel it.
So
inabaki because utajaribu. What might happen is see the library that you're using, you have put the number of written bytes, and you want that the number of written bytes you return must be equal to the number of bytes that will be requested to be written. So naively, you can retry the write operation. But now, if you retry the write operation will fail. So it's a double failure that you really don't want to like go deeper into. So Bloom filter probably used to be the structure. So Bloom filter used in a lot of big tech companies to eliminate redundant reads. Whatever that I have a key on a key log that I'm searching for a key but it doesn't exist in the key log. So the Bloom filter eliminates high percentage of reads for keys that probably don't exist. Then a buffer, remember transaction is stored in memory, then upon commit never written to the world, it's the role of the buffer to store the transaction transaction entries. Clock cache, any system can have a cache, but you can't. There are two things that in computer science, many things and caching validation.
And distributed systems.
Okay, distributed systems. So clock cache, it does two things. The caching algorithm inatumia clock. Inatumia, okay, caching in eviction inatumia something called an eviction. So unaona when you clock iko. So clock iko na arm yazunguka. Every time an entry in the cache is accessed, you increase a reference bit counter. Ukimalizia with the cache, you release it, decrement the reference bit counter. What happens is a thread that runs in the background to reclaim memory. Itapitia every block index, iangalie kama reference bit ni 0, itoe. The essence of the reference bit ni so that the background worker that's reclaiming space does not do away with the cache inatumika. Yeah. Q inasto the list of immutable name tables on this. Ikifika the 64 byte 64 KB. Ikifika the 64 KB threshold inakuwa stored kwa hiyo queue. So kuna flash queue, compaction queue. Compaction queue inasto now SS tables that are being compacted, like meaning when maintain the LSM tree structure. Manifest, think of this as a metadata structure. It only stores the SS tables na level stats. The essence of V here during recovery after crash, you want to rebuild your LSM tree, but you can't rebuild it kama hauna editor. So it's the manifest that stores the SS tables. Inakwambia which SS table belongs to which level, so that at recovery you can rebuild your LSM tree up to the levels that you develop during crash. Isolation levels, up to 5 isolation levels, uncommitted, committed, repeatable snapshot serializable. This is the fastest, this is the slowest. So ukiwana really the choice on what influences the choice, what influences your trade-offs, neither the kind of data you are serving or the kind of workload. Ukisava financial transaction, if you're running a financial system, you need serializable.